to start the recording. Yes, in trying to reconfigure my new laptop and my old laptop, I inadvertently changed the settings for how the videos were encoded to something my little laptop could not handle. So I finished class on Thursday only to discover that my video had stopped recording after 3 minutes. So for those of you who were not here, you get to, I had to redo everything, and I did that on Friday morning for those who were unable to come to Thursday's classes. So I kind of feel like I did a better job the second time. Like there's a practice effect. So in particular, the regions of significance stuff at the end, I think I did a better job explaining than what I did in class. So just that resource is there for you. But let me double check on this thing. It looks like it's encoding. Can someone from the Zoom please say hello so I can check the audio feed?
Hello.
Hello. Can everybody hear in the back? Yeah. All right, cool. We're rocking and rolling then. So first things first, I have updated the materials that go with example 1 online. So the original syntax files and output with respect to R. I sent an email about that yesterday morning, and then this morning I adjusted it again because I found an even better way to do it. Thank you to Solomon who helped me find this. I had found it independently and he helped me use it better. So this, let me get this file here and I'll get the screen share going so everyone can see what I'm talking about. That's always helpful to be literally on the same page. Okay. There we go. Hiding meeting controls. There we go. Okay, Zoomers, can you see our code in front of you? Excellent. Livers, what should we call in-person people? I think livers, does that work? Yeah. We can see the R code. So I wanted to point out where I changed it. So I have a note in here that added this morning is a new package that is called margins that somebody who loves Stata apparently decided to bring into R. That was how I found it, by the way. I asked the Google, what is the R analog to Stata margins? And this came up. So it allows you, I don't know why this is rendering so crazy, but it allows you to specify a list of predictor values for which you want predicted outcomes, the same as Stata margins. So I was able to do that to get predicted outcomes much more quickly. So that replaces all of this. So it should be hopefully less painful, and then I've adopted this in the new set of examples that I built for the next stuff. So on the web page, just to point out to folks where we're at, we've got new material starting on Thursday. So models for binary outcomes, ordinal outcomes, nominal outcomes, 2 examples, 1 for binary, 1 for ordinal and nominal, and 1 set of files for everything in terms of electronic materials. So you can grab those at your nearest convenience, and we'll talk about them on Thursday. But for now, I've started getting emails about homework questions. So should we start there? So we haven't actually gone over the model that corresponds to the last model in your homework. That's on tap for today. So if you're trying to work ahead, you may find that today is helpful. A couple questions. I think, Nathan, you sent me an email a little bit ago about significance. I mean literally p less than 0.05.
Okay, so it's not like, you know, I was mainly wondering about like the increase in R squared values because it's, you know, out of curiosity, what do you consider a significant increase in R squared? Because we talked about this in intermediate stats with Dr. LeBeau, and it was kind of interesting, like different takes on that.
I think, so the original question was, when I say significant or not as an answer in the homework, let me just find an example of that, for instance. So these drop-down choices say things like significantly better, non-significantly better, significantly worse, or non-significantly worse. What I mean by significant is literally the definition of statistical significance with respect to an alpha level of 0.05, which is what it says in your instructions. So p less than 0.05 is your cutoff. If it is equal to 0.05 or greater, then that is non-significant. And I know that you can all make that distinction. The tricky part is finding which of the 37 answers that p-value refers to. That's the hard part, is the working memory load that's involved in managing a problem like this. To answer your other question about effect size, I don't think that it is possible or advisable to make a universal distinction as to what a practically significant effect size is, because it depends on the context and it depends on the scales of the variables. So if you think about, like a COVID treatment that improves outcomes by 0.001%, right? That's significant to those, 5 or 10 people or whatever it turns out being, whose lives are now going to be saved. So I'm not going to say that an R square less than whatever is good or bad. I think it's all contextual. I just want you to know how to report it. That's where we start from. So we're not really getting into the practically significant side of the debate. This is more just about reporting the analysis. The judgmental side of it is something that I think I'm not really going to weigh on. Okay, does that answer your question, Nathan?
Yes, it does. I also was wondering too, I pulled an all-nighter last night, so my brain is fried.
That's not good.
Why don't we, I'll come back. The thought escaped me.
Okay. And then we had a question in class, and tell me your name again, please. Sophie? One more time.
It's Xiaoting.
Xiaoting?
Yes.
Okay, and you had questions about what it meant to be a bigger group difference or a smaller group difference?
Yeah, the difference for the grade experience will be the significant negative and significant better.
Mm-hmm. Okay, so we had some questions about what better versus worse means and bigger differences versus smaller differences. And I've worked on this wording because this has been a problem in the past. And so let me try to clarify. If we're talking about a treatment for instance, learning how to play mini golf better, if your scores are lower, then your treatment helped, because in golf, lower scores are better. I know that's somewhat conceptually backwards from how people are used to thinking about what an outcome means, but there are many types of outcomes in the world where smaller is better. People who study criminal behavior or psychopathy or substance abuse, like all of those are outcomes where you want less of it to have a good outcome. So golf is sort of in that same wheelhouse. So if a score is lower, that's better. In the sections where I ask about whether a slope is significant or non-significant or positive or negative, let me find one of those. Let's see, here's one. So for instance, resulting in a blank slope of experience, and the choices are positive or negative, literally the sign of the slope. So I'm not trying to say like, it's a positive thing that it made the scores go down. No, just is the slope sign positive or negative? That's all I was going for with that. With respect to the interaction terms, so in my copy of this homework, I haven't done any of the answers yet, and that's why all of these values down here are zeros. But in yours, the correct answers, or just the answers that you have, they don't necessarily have to be correct, they're going to be populating these zeros. So you'll always see exactly which coefficient that wording is corresponding to. And if you're not sure and you want to ask me, the number of the question is always right before the box. So you can say, I have a question about number 70. Here's what I'm thinking. So the ones that ask about the effects of the interaction, ask yourself, is the group difference bigger in absolute magnitude or is it smaller in absolute magnitude? So if it's a bigger group difference, then the interaction has made the groups more different. That's a stronger effect. If it's a smaller in absolute magnitude, then it's weaker. Okay, does that help answer your question? Okay. All right, other folks with questions? Okay, I'll get to Nathan's in just a second since he's already had a turn. Vladimir, go ahead.
I have a question related to the stronger or weaker effect in predictions.
Mm-hmm.
My question is, how can we know when the interaction it is more weaker or more stronger and what is the relationship with the main effect slope?
So if the slopes are in the same sign, it's a stronger effect. If they're an opposite sign, it's a weaker effect.
Okay.
I mean, it really is that straightforward. It's just that the tricky part is going to be, is the question asking about what happens to the group difference as a function of experience, in which case the group difference is the sign you want to pay attention to, or is the question asking about the slope of experience in this group versus that group? For the latter, it's the slope of experience that you want to pay attention to as the anchor point.
Okay.
And we'll go over a model that looks like this in structure today
Okay, nice.
in class. And then question in the chat, can we be 100 certain our computation results are accurate if they appear as green? They are accurate within 2 decimal places. It is possible to accidentally get an answer flagged as correct if it's close enough. But I have tried to scale these. I've learned from that mistake in the past, and I've tried to scale these to prevent that from happening. That's why the coefficients are so big. So it is unlikely that you will accidentally get the correct answer. Would you like to hear the story from where this homework came from?
Yeah.
So all of my homeworks are based on real life stories of something that has happened to me in the past, and I mine them for this purpose. But this story originated when I first went to visit my husband's family in Sacramento, California, for the very first time meeting them. And we went and played miniature golf. And oh my God, the amount of smack that he talked to his poor sisters about miniature golf. It was embarrassing. I was like, who plays cutthroat mini golf? Like, who is this person? And I made this whole story about it because he was taking it way too seriously, in my opinion. And then one time we went mini golfing with my family, and my dad, who actually plays golf, started talking about how because he plays golf, that messes up his mini golf game, and making excuses along those lines. So I made up this whole story about the deleterious effects of trying to play regular golf and mini golf at the same time. And that's where the story came from. So, and the other piece of this, this is sort of an inside joke. I have to say it for it to make sense, though. So I got to get the wording here. The mini golf enthusiasm scale, the abbreviation for that is the MGUESS, because that's what I say if someone says, do you want to play miniature golf with me? I say, I guess. Like, if I have to. So, anyway. Nikki says that she is the undefeated champion of mini golf in her household. Congratulations on that. I came in last the last time I played mini golf, which was over Christmas when I was on vacation with my family. So my mother and I both tied for last, I believe, and I'm quite okay with that as my legacy. Okay, I can handle that. And then there was Huey, who was doing the version of mini golf where he just keeps hitting at the ball continuously. Like, he doesn't actually wait for it to stop. He just kind of traps it, you know. Does everyone know what mini golf is? Is this a game that you've played before? Okay, yeah, it's just a silly putt-putt thing, but anywho. This is the story for this week's homework. So other homework questions for right now. This is not due until next week, so I'll ask again on Thursday. No? We're good? Okay. Well, then I will put this stuff away for right now, and I want to pick up with a few slides and then the rest of example 1. So let's do that. And I'm going to shut down all unnecessary files here so that my little computer doesn't get overwhelmed. Double check that I'm in fact still recording, which is always helpful. All right, so I'm on slide 22 of lecture 1, interactions involving categorical predictors. You can do it, there we go. So last week, because today was garbage day. That's how I know. That means it's Tuesday. Last week, we talked about interaction terms between 2 quantitative predictors that were each characterized by a linear relationship between the predictor and the outcome. So in a situation like that, for instance, when we had a chronological age and grip strength as the 2 variables that interacted in that model, each of those had only one slope to describe its effect, and therefore the interaction of the 2 required only one slope as well. So that's the simplest case of a moderation model. If you have a predictor whose effect is characterized by more than one slope. So for instance, if I had had a piecewise linear effective age or a quadratic effective age that took multiple slopes, or as it has on this slide here, if I have a categorical predictor, then fitting a moderation model with that predictor is going to require more than one interaction slope at the same time. So it adds a level of complexity, but it's the same in principle as what we just did. So I want to make sure that we have a concrete example for you to follow, such as a 4-group variable with 1 control and 3 treatments, just like in your homework. So let's say that we set up a 4-group variable with 3 dummy codes using indicator coding, where the control group is the reference, where all the new variables are 0, and then each of these refers to the difference of how that treatment group differs from control as the reference. If I wanted to have an interaction between this 4-group predictor and age, that requires 3 interaction terms. Even though conceptually, if I look at this model, conceptually what I have is group, age, and their interaction, like 3 ideas. To pull that off, group is 3 betas here, and group by age is also 3 betas. So one thing that we have to do then that's different because of this is that we can't stare at the p-value for one interaction term and say that it made the model better, because there's more than one. So in general, if you add only one thing to the model, and that one thing that you added is significant, what that means is that the change in the R-square created by that one thing is necessarily significant. It's a one-to-one correspondence. If you add a predictor and it's significant, then you have increased the R-square. But if I add multiple predictors, then I have to lump them together in order to really answer that question. So the group by age interaction requires 3 slopes. That's going to require a multivariate wald test. So an F-test or a chi-square, putting the 3 together to answer that question as to whether there is a group by age interaction. The other thing that's tricky about this is that I can't look at the slopes for beta 1, beta 2, and beta 3 and talk about what happens between the groups. I have to keep track of what these groups are conditional on, which is age 85 in this model. So these are group differences among 85-year-olds specifically. Likewise, beta 4 is not just the slope of age. In this model, it's the slope of age in the control group, because that's when the rest of this zeroes out with the group dummy codes. Oops. And even though this model only gives us group differences conditional on age 85 and an age slope for the control group, it gives us every other combination as a linear combination of the fixed effects. Okay, with me so far? Good? Zoomers? All right, excellent. So here's my model again, and here's some algebra. So the model implied effect for each predictor then. The effective age in the control group looks like this. The effective age in the treatment 1 group would just be beta 4 plus beta 5. So this is directly analogous, by the way, to experience and golf training groups. Cough, cough, homework question analogy, cough, cough. So this is the logic by which the model tells you what the effect of the interacting quantitative predictor would be in any group. And if you can figure out what the effective age is in each group, then these are the ingredients that you need to figure out how the effective age differs between each group. So that's the next set. That's coming, not quite yet. We have the simple effects of group for any age. So the model tells you each of the differences of the treatment groups relative to control is the reference for 85-year-olds. You can figure out what those differences would be for any age. And here are the missing comparisons for treatment 1 versus treatment 2. So it's ugly, but it's possible. So the key to getting all of this right is to figure out just these first parts here. How does the model give you the effect of the quantitative predictor per group? And then how how are the group differences conditional on the quantitative predictor, and then from there you can figure out the differences as literally the subtraction of these things. Okay. Three-way interactions are ugly. I'm not making you do that yet. Okay, so stare at this for a second and tell me if you have questions on how I got here.
Lisa,
Yes, sir.
my question is, how can we get the last contrast using the R code that you provide us? T2 versus T3?
So all of these in R would be GLHT statements, where you would have your combination of that, the string of numbers basically are the multipliers.
Yep.
And so for instance, you would have negative values attached to all of these because if you multiply the negative sign through, that's what happens.
Okay.
So if you get this part correct, then you can use the difference of those statements to create the linear combinations.
Yeah.
Like literally once you get the zeros and ones for one line and the zeros and ones for another, you can subtract those zeros and ones and you'll get to the right place.
Okay.
Yep, and I'll show you an example of what that looks like in all three programs today. Okay, what about three-way interactions? Not right now, but it's the same principles. So it's the same deal. Each of the two-way interactions, in this example, x and z, w and z, x and w would be conditional on the third being 0. So in addition to having simple main effects, you'd have simple two-way interactions. I don't think we're going to work through that this semester, but I just wanted you to have that. All right, so that's the algebra on those. Okay, now we're done with this. And this, by the way, is the extra slide that I added. You're welcome. We had a question about effects coding. Ask and you shall receive, folks. These lectures are not written in stone. So this is a page from the Darlington and Hayes General Linear Models book that I'm using in the other class. I also added to your guys' syllabus because I think it does a really good job explaining a lot of things. And this is effects coding in the bottom here. Under an effects coding system, the average of the four groups is the intercept. And so in the context of interaction terms, to me, this is weird. Because if you were to do effects coding, say, for the model we just looked at with group and age, the main effect of age that's given by the model is not for any of the four groups. It's for some kind of average across the four groups. And literally no one is like that in your study. Everybody belongs to only one group. So to me, this is not helpful. But that's an opinion, right? You are allowed to set up your model however you want. And these are all equally correct so long as you don't mess them up. And by that note, I have never, ever attempted to do this thing, whatever the hell this is. Helmer coding, just no. If you know how to use estimate statements, GLHT statements to get linear combinations of things, you don't have to have an elaborate coding system because you can always ask for whatever additional differences you want. So yeah, no to this. All right. Exit on that. Any questions before we jump back to the example? Okay, then moving right along. So we're in example 1, ready to do the very last model. So let me find where we were. By the way, as I'm going through this stuff, if you find yourself trying to write down all of my interpretations, please stop. Do you know why? Because at the end of each of my handouts, there are words. So this is how I would write up the models in this handout to create a result section. This is plagiarized near identically from chapter 2 of my book, but I do this for all of my handouts. So if you want to know how I would say this, this is how I would say this. So you don't have to worry about catching everything. All right, but we're not there yet. Sorry to make anyone seasick here, but here we are. So we are picking up on page 16. 16 of 22. Not even a personal best. I think my largest handout ever is somewhere in the 50s. I take it as a personal challenge to try and kill all the trees. But we don't actually print things anymore, so I'm not really killing trees. Anywho. Okay. So we are adding to the model we left off with on Thursday. So just to remind you, cognition is our outcome. These are fake older adults that I am examining. We have main effects of age centered at 85, grip strength in pounds centered at 9 pounds per square inch. We have a gender variable that is binary, in which men are the reference and women are the alternative. And we have dementia group, which is none versus future versus current. None is the reference. So dem NF gives me how future differs from none. Dem NC gives me how current differs from none. Last time on Thursday, we added this interaction term between grip and age, and that's going to hang out because it's significant. And then we're going to add an interaction between gender and dementia group as a concept, but that interaction requires 2 slopes because dementia group requires 2 slopes. So if dementia group had 5 groups, how many slopes would I need?
4.
4, yep. So I would need 4 slopes for the differences across the 5 groups. That means anything that 5-group variable interacted with would also need 4 slopes. Here's the answers. So this model would be otherwise considered probably like an ANCOVA or something. Like this part right here is adding this creates a 2-way analysis of variance of gender as one grouping variable and dementia as the other. When I learned ANOVA as an undergraduate at the University of Nebraska, this is how I learned it. We had tables of boxes like this. We never had any models. And these outside marginal means is what we called them. Inside here, we called these cell means. So the predicted outcome for each combination of the 2-way interaction between these categorical predictors, you have a specific cell mean. So when paired with the intercept, the 2 simple main effects of dementia group, the simple main effect of gender, and then the 2 interaction terms, that's 6 things, will perfectly recreate these 6 means. So as long as you have as many fixed slopes as you have possible unique means, these will all be perfectly predicted. The question is, how are these things different? So I'll show you in a minute that we're going to have a significant F for this interaction term. The question is, where's the difference? Is it how men and women differ from each other, differs across these groups? Is it how dementia group differences differ in men than in women? Is it both? So the tricky part for these designs is figuring out exactly what the pattern of the interaction is, because we have to understand not just all of the simple effects that we want to write about, but how those simple effects differ from each other. And the latter is the tricky part that I never learned until far too long that I want to focus on today. So classic ANOVA would return marginal main effects out here as these differences. To me, those are useless, because if you have a significant interaction term, by definition, that means that whatever patterns you have out here don't hold. They might be in the same direction of different magnitudes, they might be of different directions, but they don't hold. So to me, finding out whether or not on average there are group differences across dementia groups averaging over men and women, or on average, if there are differences between men and women averaging over dementia groups, neither of those things is interesting to me. So I'm not going to do them. I'm just not. So we're staying inside the cells here. And the model is going to create all of the differences that we need to talk about these 6 cell means. Okay. Questions so far? All right, let's do the algebra. The model tells us how to get the sex slope, the gender difference for any dementia group. The rules are, what do I do first if I want to figure out how the model says men and women should differ? How did I get here? What did I do?
To gather the slopes related with the variable that we are interested in.
Yes, I gathered the slopes that are related to the variable that I'm interested in, meaning that the only terms that are possibly relevant in figuring out what the model says the sex slope should be, they have to have that variable in it. So a common mistake that I see people make is because they get hung up on the second part of the sentence, for dementia group. And they want to stick in the main effects that have to do with dementia group because it'll say for this specific group. But the main effects of dementia don't go in there because they don't have anything to do with the gender slope. So only the terms that have the slope in question, factor it out, and here's what's left. So this is how the model tells us what the gender difference is going to be in any of these three groups. So that's whether those two numbers are different, those two numbers are different, or those two numbers are different. Other way, same idea, backwards in terms of moderation. So the model also tells us how the dementia groups differ from each other for each gender. So if I have the same premise, if I'm talking about none versus future, here are the terms I need. So I'm going to factor the one out that I need. Here's what's left. If I'm talking about none versus current, those are the ones that I need. Here's the result after I factor out the one that the slope is for. These are the ones that are going to be directly given by the model. The third is a linear combination. But if I've already figured out that this is the part that's none versus future, and this is the part that's none versus current, then it is none versus current minus none versus future. So the one that's missing is already given to you as a function of the ones that you have. But note the minus sign. The minus sign you have to distribute across all the terms in the brackets. Is that the right word for that? Carry it through? Math people, can you confirm? Distribute the minus sign? Carry it through? I'm being serious. Is this what it's called? Is that the right words? No one's answering me.
I think so.
I thought so too, but I'm prone to saying the wrong thing. I was in rare form this weekend. Would you like to hear a very quick anecdote about my weekend and how silly mistakes I can make? So I spent most of the weekend fighting with R in preparation for your materials on Thursday. And I had gotten to the point where I figured out what I was going to do, and I was starting to do the code in R, and I couldn't get the variables created. Like the same type of code that I had, I was like, how did I forget how to center a variable? Like, why isn't this working? And I look at the log, right? It's all blue. There's no error messages. It's just not doing it. So Jonathan wakes up. He stumbles into the kitchen, bleary-eyed, getting his coffee, and I'm like, can you help me with R? And he walks over. Okay, he looks at it. He goes, those are capital letters, and walks back over to the coffee. It's like, you're right. Yes, thank you. Big reaction from the Zoom audience here on this one. I had a data set whose words, the variable names, were entirely in capital letters, and I was typing them in lowercase. And so R's like, I don't know what the hell you're talking about. That's not the same variable. So yeah, that's where we're at right now. I'm not sure what the difference is between capital letters and lowercase letters, and I had to ask for verification. Likewise, this is distributed, right? That's the right word. So that means that this spot in the zeros and ones needs to be negative, and so does this one. So that's one thing that's easy to screw up, is don't forget to distribute the negative. Okay. So going through then, how do I get each program to do my bidding with respect to these things? So each of these is a simple effect of one predictor at specific levels of the other. The very last step will be to get the differences between these two. Those are coming. All right. So SAS. Here's my model. So asterisks to denote the interaction terms. Contrast gives me my main effect of the interaction. So whether or not the two slopes that make up that group by gender interaction significantly add to the model. So if this F-test that results from this contrast statement is significant, that necessarily means that my R-square has increased significantly. There is a one-to-one correspondence there. Within each dementia group, I can find out what this simple effect, within each gender, I can figure out what the omnibus effect of dementia would be. So this is a 2 degree of freedom test. So note, zoom in on this, the comma. You've all seen those memes about how commas save lives. Like, let's eat, grandma, or let's eat, grandma. Commas save results. So this is one thing right here, and this is a second thing, because there's only one comma separating them. So I'm asking for the effect of how none versus future, the effect of how future differs from none, and the effect of how current differs from none. And because these interaction terms are set to 0, that's what makes it specifically for men. Likewise, if I want to know what is the omnibus 2 group F-test for whether there are group differences in women, this linear combination gives me how future differs from none in women, because that's when the interaction term kicks in here. And this one gives me how current differs from none in women as well. So those are additional results that you can ask for if you want to know if there is an overall effect of dementia group within each of the moderating values. Here's how I am going to get my fake people. So I am asking it to create predicted values and standard errors for everyone in my data set. If I hadn't done that, then here's how I would get the cell means first. So even if you have a way to get the predicted means, I would actually recommend going through this step. I know this is a lot of typing, but it makes the underlying logic that much clearer. So this is how the model tells me what the adjusted mean would be for anybody in that 2x3 combination. So these are what we refer to as cell means, and I call them adjusted cell means because without age and grip anywhere in these lines, that means I'm holding those cell means at age 85 and at grip equals 9. So when you are creating a Y hat, cough, cough, homework question, always the intercept goes in here. To create a predicted outcome, at a minimum, you need an intercept because that's the predicted outcome when all your predictors are 0. So you're nothing without that. Then the values that go after that depend on who the predicted outcome is for. In this case, it is for a man who does not have dementia, and that's why this is 0 for a man. Not having dementia makes these 0, and because 0 times 0 is 0, these are 0. In contrast, if we look, say, at Y hat for women who currently have dementia, starts with an intercept, pick up the gender simple main effect because we're talking about women. This one is still turned off because it's the current group. So 0, this variable is coded 0 if it's current. This one turns on. And so because of these two, 1 and 0, the first interaction term stays 0. Because this one and this one are both 1, the second interaction term turns on to 1. So the interactions when you're creating predicted outcomes are just the multiplication of what you already told it with respect to its main effects. Okay, with me so far? Now if we do the sex differences. What is the difference between men and women who have no dementia? Well, I can go up to these two lines. The difference of those first two lines is the result that I get right here. So the way that I've coded it is such that it's men versus women. That means women, the second line would be first, okay? So this line right here is first. Subtract from it this line. The intercepts cancel. This goes to 1. This stays at 0, this stays at 0, and those stay at 0. And that's why this is the result. Let's do a harder one, sex difference for current. It is that line minus this one. So I end up with, what do I need for the sex difference? I need the slope for it to begin with. And then I need the group that it's for. Turns on with the interaction term. Okay. I know I'm highlighting and saying this and that a lot. Any of that you want to hear again? And I will show you the other programs in just a second. But this one I think is easier because the labels are right next to the numbers. And in R, that is not the case, and it makes it harder. Okay, then we go to dementia group differences. Future versus current. That's the hardest one. Let's do this one right here. How did I come up with -1 and 1? Well, let's find the relevant groups. We have, this is future versus current in men, which means it's that line and that line. If I take the second one that's highlighted right here and subtract from it that line, that's why I ended up with -1 and 1 right here. If I did the same thing for the women, then these are the two lines. I take the current line and subtract from it the future line, and then I end up with that combination right there. So these 6 cell means, even though you can get them via predict or any other easy way, writing them out gives you the ingredients for literally everything else. So now I have the sex differences per dementia group, and I also have the dementia group differences per sex. One last step. An interaction term in ANOVA language is a difference of a difference. So it's either going to be how the gender difference varies by dementia group, or how the dementia group differences vary by gender. And I have written them out both ways so that you can get a sense of how the interaction creates both interpretations. So if I want to know if the sex effect differs between none and future, what I'm asking about is a comparison of these two lines, right up here. And what makes them different is just this one interaction contrast right here. Likewise, if I want the sex effect differs between none and current, then it's the current line minus that one. And that gives me this one. And now down here, if I know how none and future's simple effect differs from none and current, then a combination of this one and that one gives me this one. And the other way to spin it then is how the dementia group differs between men and women, and it's the same contrasts. So in terms of interpreting the interaction, these are what you need. Because if you have a significant gender effect in this group and one in that group, that isn't an interaction term. An interaction term is a difference of a group difference. So this same setup, by the way, can be used to guide the code that you would write for your homework. If you swap out golf group for dementia group, add another slope, because golf has 4 groups instead of 3, and if you pretend that sex, as my moderator variable here, is experience. So treat sex as the quantitative predictor of the interaction, and treat dementia group as the categorical, and then it maps very closely onto your homework. You just have one more set of slopes involved. Okay, questions on the logic? Okay, do you want to see it in the other programs first, or do you want to go through the numbers? What would be more helpful to do next? Anybody have a preference?
Numbers, I think.
Numbers?
Yeah, interpretation.
Okay, we got 1 vote for numbers. Anybody else want to weigh in?
Well, I had a specific question on Stata when we do this, but I can wait.
Okay, all right, we'll do numbers, and then we'll look at how the other program's set up. But it's the exact same principle in terms of zeros and ones. It's just how you enter it into the package. So here's my results. This table, by the way, this is the last time you'll see this semester. Say goodbye. Sums of squares, it's been nice knowing you. Thank you. But we're not going to have this anymore because we're leaving sums of squares land. On Thursday, we're heading into maximum likelihood land. But no worries. We can still ask whether or not we have a significant model. You just have to ask for it yourselves, because it's not going to be spit out for you automatically anymore. But I got 8 slopes in my model. I could have added 541 more. So yes, my model is significant. How good of a model is it? Well, it accounted for about 30% of the variance in cognition. So. Now, relative to the things that we added relative to the previous model, this right here is the F-test for the 2 new interaction slopes specifically. So this tells me, this F value right here tells me that there is a significant sex by dementia group interaction. Doesn't tell me what kind or how or for whom or whatever, it just, that's it. And that's why we have to go to the trouble to break this apart, because that information by itself is not enough. Now this is a start. Okay, are there differences across the dementia groups in men? Yes. Are there differences across the dementia groups in women? More yes. So I'm just eyeballing these. It looks to me like what we're going to find is a bigger difference as a function of dementia in women than in men. And I can go back up to my cell means table and look at that too. So if I look at these 3 differences, dementia is bad for you, that's clear. It looks like it's more bad for you if you're a woman, though. Because this is a big drop down to 6 for this cell mean in particular. Question?
Did this data set have equal representation of men and women?
Approximately.
Okay.
Yeah, if the group sizes were unbalanced, then it would be much harder to eyeball these results. But yeah, I made them up, so it worked perfectly. All right, here's my parameters. So these ones, let me see here. Intercept, age, and grip, and the interaction, we did those last time. They all have the same interpretations, pretty much the same values. So it looks like The age by grip interaction makes the grip strength effect bigger in older people. This is a more positive. Likewise, the negative effect of age is made less negative in stronger people. So that's a weaker because the signs are opposite. We can focus then on the new parts. So let's start this way. And I'll make these a little bit bigger. By the way, this out here with the betas, this is not SAS. This is me being nice. So if you're hoping that SAS will interpret your parameters for you, you will be mistaken. This is Proc Lisa, and this is why I have a job. Because I have figured out what SAS is trying to tell me, and now I can tell you guys about it. Job security, because nobody else wants to learn this but us. So here's my simple slope for gender. The coefficient itself is minus 2.8-ish. So who's higher, men or women?
Men.
We got one vote for man. Anyone else want to weigh in? The coefficient is negative. Men are the 0 and women are the 1. So yep, the negative applies to the score for women, bringing it down. That means men are higher. So it looks like women have a deficit relative to men. And in which kind of person is this deficit of 2.88? Conditional on what? For whom is this the gender difference? What kind of people?
And like as compared to the reference?
That's where I'm going. So sex is part of an interaction with dementia group. Which group is this the gender difference for? No dementia, correct. That's what the N means in my variables. It stands for none. So the none group is the reference because they have a 0 for both of my dementia slope variables, slope predictors. So this is the gender difference among people without dementia. Now what happens to it as a function of the interaction terms? So the first one is going to talk about what happens to the gender difference in the future group. So there's a negative slope paired with a positive interaction term. So what is the interaction term doing?
Softening the blow.
Softening the blow. That's a very nice way of putting it. Yeah. This is a less negative, or the interaction is creating a smaller sex difference. Non-significantly, but that's the direction of it. So what is the gender difference predicted to be in the future group then? This is something that folks commonly mistake. This number right here. Is that the gender difference in the future group?
No.
It is not. What is it?
It is beta sub 3 plus that interaction term.
That's right. To get to what the gender difference is in the future group, we need that one
Plus that one.
plus this one. The 0.16 is how the differences differ. So you put them together to get to what it is for the future group. Likewise,
Lisa,
that one and that one. Yes, sir.
in this case, so that interaction term, it is a weaker effect
Yes.
on the main slope?
Mm-hmm.
Okay.
Yep, I'd say it's weakening it. It's not significant, but that's the direction of it.
Yeah, okay.
Yep. Yeah, in this class, you're going to see me almost nearly always disregard p-values because I know you know what that means. I want you to know what to do with the numbers. Because I really hope this interaction is not significant so I don't have to interpret it is not a valid response. Not that any of you would do that, but I have heard that before from students, and I can't say I blame them, but I want you to know what to do with it. How about this one? What happens to the gender difference of about -3 in the current group?
It is more negative.
More negative. It is bigger, stronger. The groups are further apart. So there is a bigger deficit in women with current dementia. Significantly this time. So the difference, if I'm eyeballing this, is about -3 plus -8. So like an 11-point difference or so. Now what I can't do is eyeball these things and tell me whether or not they're significant, because there are sample size differences across the dementia groups. In particular, 70% of the sample has no dementia, and the other 30% are spread across the other groups. So I need to have the significance test associated with this difference to make sure that it's actually significant. And you can kind of get a sense of that with how large the standard errors are for things related to these other smaller groups. Okay. Going the other way then. Starting with the dementia group difference. People with future dementia are 6 points lower in men. What happens to that dementia group difference in women according to this interaction term? Stronger or weaker?
Weaker.
Weaker. Yep. They're an opposite sign. How about that one and that one? Stronger or weaker? Stronger. Same sign. So yeah, the difference between none and current in men is like 12 points. The difference between none and current in women is like 19 points. I think we got them all. And then here's the actual numbers. So these are the simple effects of sex per group. These are the dementia group differences conditional on gender. And then the last column here, these are the goodies. These are the differences of the differences. And so I've inserted the significance into my table here. And I have grayed out the stuff that's marginal because I don't care. So you can talk about how those two numbers differ differently than those two numbers. Or you can talk about how those two numbers, the difference of 6, don't really differ from those two numbers. Where the action seems to be is in that contrast versus that one. In men, there's a 6-point difference between future and current, whereas that difference jumps to about 14 in women. And here's the pictures. So we can talk about the effect of dementia group differing by gender, or we can talk about the gender effect differing by dementia group. Question?
Yes, it is about the interpretation of the table, the previous one.
Yes.
In this case, for example, those numbers in the last row, -5 and -13.
These?
No, the last one. Yes, the -13 and -5.
Oh, the other one.
Men
Got
and
it, this way.
women.
That
How
one
come-
and that one?
Yes, how can we interpret those numbers?
Those numbers reflect, so the -5.9 is this one versus that one.
Okay.
And
yeah.
the -14
Uh-huh.
is that one versus that one.
Okay.
So the interaction term tells us how this difference of 6 differs from this difference of 14. And that gives us the interaction coefficient, which is about 8. Or 8. Right, there it is, right there.
Yeah. Thank
Yep. So in your homework, by the way, I would recommend a table. I would recommend building yourself a table that looks something like this, where you've got all the effects. And then when I ask you, is this effect bigger than that one or smaller, you've got the numbers. And then it's just a question of whether it's significantly bigger or not, and you've got the p-values and the standard errors to help you with that. Okay. Ready to see the other packages? How to do this? All right. Stata, folks. So here are the two new interaction terms. One thing to keep in mind that may differ across your versions of Stata, but if you want a line of code to wrap multiple lines, you have to do a line continuer. So don't forget that thing. Otherwise, it thinks your model is done when it reaches the end of the line, and it will be confused if you keep typing down here, because it's like, what are you talking about? Regress is over. So the 3 slashes is a line continuer to make it keep going. Not to be confused with only 2 slashes, which is a comment. See, it's not just SAS. Every program has its little, tips and things that if you learn it, someone will pay you. So the analog to get F tests, that's my test statement. So if I want an omnibus effect of whether or not I have a group by gender interaction, so those two slopes lumped together, then each slope goes in a set of parentheses set equal to 0. So the parentheses denote the numerator degrees of freedom. The line wraps automatically now. And Nikki says, that's good news, because that's super annoying, but I have like 4 different versions of Stata across all my machines, so I always try to make my code backwards compatible. Question?
So could you also do, instead of saying that equals 0 and that equals 0, could you do the first interaction term equal to the second interaction term?
That would be a different hypothesis test.
Okay.
That would be whether the none future difference is the same as the none current difference. Like, okay. So that's that would be like a model constraint of how the interaction could be. This is just saying, what is the extra contribution of these 2 terms? Give me an F value for that. And so if this result is significant, then the increment to your R square has to be significant. And then these are the omnibus within group comparisons. I don't think I asked for any of that on your homework. Here are my dear friend margins. So these are your predicted outcomes for each of the dementia groups. I wrote 3 different lines because there's only some possible combinations. So there's only these 3 combinations that are possible, and so that's why I wrote them on 3 lines, so I wouldn't get extra combinations that didn't make any sense. Here are the set of gender differences. So we have each of these starts with the thing you want the slope for, and then after that you fill in the value of the moderator that you want the slope for. Likewise, these are the simple effects of dementia group per gender, and then the differences of these differences are your interaction slopes down here. So it's the exact same pattern of 0s, 1s, and -1s as I showed in SAS. I think that's, and pictures. Here's some code to make pictures. Okay, Stata folks, any questions on that?
So when I ran the linear combination command, it was adding in, because I defined group in the homework as categorical with like I dot.
Oh yeah, if you do it that way, this isn't going to work.
Okay. Because then I did like 1 dot group, 2 dot group, 3 dot group, and then I was adding in like, and I was like for the control, it was like 1b dot group. Mm-hmm. And so what does that be?
Baseline.
Oh, okay.
Yep. Yeah. If you do I dot in Stata or make a factor variable in R, then this code isn't going to work.
Okay.
So if you want to figure it out that way, Godspeed. I actually have an example of that in 6242, the very last example of that class. I did this same model 3 different ways to talk about how the code has to change as a function of whether you let the program create your categorical predictor. So I would refer you to that example if you want to learn how to do it. But that won't work in a lot of generalized models, so that's why I'm not doing it that way. And our folks, Okay. Know that I am with you in the pain that is this process, because I had to write it out. And I had to do your homework too. So I had to make sure it works in all 3 programs. So I do each of your homeworks 3 times. So the model itself, here are the interaction terms. And this is the order in which they will show up in your output. It will list all of your main effects first, followed by your interaction terms. And this order is critical to understand to get these things right. So these zeros and ones are the multipliers of the betas in your model. So they correspond to the zeros and ones in the SAS code and the Stata code. It's just that the order of these things is as given by your fixed effects. So let's see here. Here is this one. I want to make sure I show you this one. I asked for a joint test of whether the 2 new interaction terms were significant this way. So you can set it up with these contrasts of zeros and ones, or you can write it out. There's a couple different ways to do it, and sometimes one is easier than the other. So this is how I tested the contribution of these 2 interaction slopes simultaneously to get an F-test. And then these are the simple effects of dementia group within each gender. So the 2 degree of freedom contrast for each of those. Here are my cell means. So this is the thing that the new margins command that I showed you can replace. But I would still maybe go to the trouble of writing it out so that you can get the rest of these patterns right. Because everything starts with how the model gives you a mean for each combination. Once you know how the model gives you each of those cell means, then this is your answer for how to get the differences. So these lines right here start with a 1 because there is an intercept at a minimum in every single predicted mean. And then the 1s turn on that go with each of the predictor variables in turn. And then here are the dementia group differences. Note that I have spaced them out so they stay aligned. I would recommend this so that it makes it easier on yourself to check for errors. And note that some of these never get used, so those 2 and that one stay 0 because those refer to the effects of age, grip, and their interaction, which are not part of today's story. And so then here are the interaction contrasts that we end up with, the difference of the differences. And you'll note that all of the main effects have dropped out by this point. All questions involving whether one group difference is different than another group difference, that's all interaction terms. So the first 2 tell you about whether the gender difference differs between none and future. The second 2 tell you about whether or not the gender difference differs from none and current. And then the last 2 give you current versus future contrasts as the linear combination of these terms right here. And then words, which is good because it's 140. All right. So questions on any of this? Zoomers, let me start with you. No? Okay. In-personers?
So, for the interaction term, so for this example, it was the moderator was sex. So would you, if you wanted to compare interaction terms, like we were like in the last 2, like letter C, would you say would the question be, does sex have the same effect on both groups?
Yeah.
Okay, and then if we did this and it spit out the same value for both, then we would say that the interaction is the same for both current and future dementia.
Not quite.
Okay.
I think what you would say then is that the simple effect is the same.
Okay.
So this question, like if we do this one right here, the root of the question is the difference between men and women. Is that gender difference the same in the none group as it is in the future group? If that gender difference is the same in both groups, There is no interaction.
Okay.
An interaction is a difference of a difference. I know that hurts. And that's probably why I never did this as an undergraduate. And instead, I had a table that looked like this to work with. All right, other questions? You feel like you can do this? Maybe? Willing to give it a try? Going to find out. Exactly, that's all you can do. And what are the rules if you get stuck on one question for more than 15 minutes? What do you do?
Send you an email.
Yeah, email me. Walk away. Walk away and email me. Just a word to the wise, though. If you're working with the virtual desktop, save your work before walking away, because it will disconnect after some period of time and your work will be lost if you haven't saved it. Some people are nodding. So a few folks in the other class found that out the hard way. I know. So make sure that you save whatever you're typing into before you walk away. But please don't be ashamed to ask for help. If there is a mistake to be made, I have made it. I can guarantee that, particularly when it comes to our code, for instance, where you have like the wrong place here, or the wrong set of parentheses, or you're missing a comma, or in SAS you're missing a semicolon. I've made the mistake if it's possible to be made. So let me help you if I can. Office hours on Zoom from 3:30 to 4:30 today and Thursday as well. So, okay. Anything else before we call it a day? No? All right. Then, oh, we got one more question. Go ahead.
Yeah, a quick question. In the last table that you have
Yes.
in the example, we can see the mean differences.
This table? Or what page are you referring to?
Last page.
The last page.
Yeah,
Okay.
the results.
Yes,
in
this
our-
table.
Yeah,
Yes.
in this case, for example, the last results, it says future versus current diagnosis. So
Mhm.
that minus 5.91, it is the difference between future and current diagnosis within men,
That's right.
and the minus 13 within women.
That is right.
Yeah. How can we interpret that minus 8.04? That's,
Minus 8 is how this minus 13 differs from this minus 5.
yeah, but what is the interpretation?
That is whether dementia has a bigger effect on women than men. The effect of dementia is bigger, more negative in women by 8.
Okay.
Dementia is more worse for you if you're a woman.
Yeah. Okay. Yeah.
That's the story.
Okay. Yes.
Yep. Okay, other question?
So, because I made these factors, I somehow arrived at the right answers, but which I'm a little scared about. But are you if you do it that way, are you essentially letting Stata dummy code for you?
With IDOT?
Yeah.
Yes, you are.
Okay. So, but we should get in the habit of doing it ourselves, because that won't work in future.
It won't work necessarily.
Okay.
I think most of Stata has IDOT capabilities, but not all of it. The reason that I don't do that is because it's less transparent what is happening behind the scenes. And because like if you put in group by age, for instance, or group by whatever, like you write one term, but it's actually creating 4 terms in the model.
Yeah.
So that like asynchrony is troubling if this is the first time you're seeing how this works.
Well, and I when I was doing the test functions, I was definitely running into issues, because it was saying, oh, you can't do that with a factor. IDOT is not allowed. So that's probably
Yeah, then you get into situations where it won't and then it marginalizes too in a weird way. So like it's hard to tell which things are specific to the 0 versus which things are averaged over the interacting variable.
Mm-hmm.
There's some inconsistency in what happens. But if you want to see what the code would look like, 6242's example 7 I have the same model 3 times to make that link. All right. That's it, folks. I'm going to stop recording. Thank you for being here. I'll see everybody on Thursday. Bye.